So today we're going to do what's going to be part 2 of our 4-part series on our energy savings or energy conservation series. As you know, last time we did a fantastic one with Steve Hussman on steam. This one will be on pneumatic, and the next one after this will be for electrical. I believe it's going to be related to VFD drives. And then in April, we're going to have a roundtable discussion. We'll have everybody that has presented come back. We'll have some breakout rooms so that way everyone can then kind of bounce in and out of those rooms, ask more detailed questions or dig a little deeper into each topic and subject. For this one, we're graciously and very lucky to have John Jensen and Johan Dieger from the Energy Conservation Group from SMC Corporation. Between the two of them, John is he's provided consulting services in various pneumatic systems. He's a certified machine safety expert, and he manages the machine safety group there at SMC Corp. He's also a past president of the International Fluid Power Society. And prior to that, John served nearly 10 years in SMC's North American, as an SMC's North American training manager. So yeah, Johan actually works within that division with John, and he will be the one giving the presentation today. So with that, I will hand it over to Johan. And just so everybody is aware, we will be monitoring the chats. And if anything comes up, we'll try to answer those as those pop up, and we will make time afterwards for any questions as well. So, Johan, go ahead and take it away.
Thank you. Hi, good afternoon, everyone. As was mentioned before, we with SMC, with the Energy Conservation Department, and we will just have a very informal discussion today. What we're planning to do is just to discuss how you can almost conduct your own smaller scale energy audit at your facility or at your customer's facility, and just the things to look for. We do this quite a lot. We do quite a few assessments every year for customers, and we're just going to highlight what we see in these factories, what we walk past, what to look for, the tools and information you'll need to do your own energy conservation assessment. And yeah, just to, it's all the low-hanging fruit. We're not going to mention anything expensive. We're not going to discuss what to do with your compressors, you know, how to set them, things like that. It's all low-cost, quick fixes, things to look for. Like I said, the low-hanging fruit of energy conservation. So we'll just dive straight into it. Just to quickly mention and why this is so important, why saving air is so important. If you look at the bottom part of this little diagram, you'll see the heat loss of the electricity on a compressor is 85% of the energy was lost just, you know, to generate it. So the actual electricity being transferred into pneumatic power is only 15% of the power being consumed by the compressor. So already you're losing 85% of the energy that goes into the compressor. Of that, if you look at the top, the green section, we'll break that 15% into 4 smaller sections. Production will get the biggest portion, normally about 50%, depending on a plant. And then you'll have your inappropriate uses, your artificial demand, and your leaks.
Lowercase h, lowercase a, lowercase r. 2032.
Someone has a mic on. Anyway, so yeah, so we'll break up. We'll look at leaks. We'll look at the artificial.
Sandwich.
Sorry. So we'll look at artificial demands, we'll look at inappropriate uses, and we'll break it up into where that, how to find those leaks, how to find those artificial demands, how to find those inappropriate uses. So when you start your energy assessment, we normally break it up into 5 pieces when we do it. If a customer does it themselves, they would normally only look at the middle 3, you know, organizing it, you know, getting all the tools, getting all the information together. They'll also look at, you know, obviously then they'll conduct it, and then they'll analyze the data afterwards. The objectives that we'll normally look at when we do this energy assessment We look at determining air quality. Is the air clean? What's the dew point, the water in there? Just to look at the general quality of your air. It's like on a car. Your oil needs to be clean or your engine won't run. It's the same with air. Your air needs to be clean or your components won't last. We'll determine a baseline. We'll see at the minimum requirements that your factory would need to run, or the minimum requirements specific machines will need to run efficiently, and see how low we can get that. We'll also look at inefficiencies. Where are the inefficiencies in the factory, and how can we, make those applications or those machines more efficient. We'll look at the large consumers of air. That one machine that uses a lot of air, why is it using so much air? Or those big vibrators that run to shake a hopper. Is there a different way that we can do this? Can we just, have a cylinder with just impact on it, for example? And then we'll provide the solutions for all those different objectives. To break it down, those 3 bars, if you remember right in the beginning, actual production on average is only 50% of the air that's being produced by the compressor. 30% goes to leakage, and 20% goes to non-productive uses, which is all the NIs and the Vibrators and things like that. So to really break it up, leakage, that is faulty components. Non-productive, the components aren't faulty, but there might be a better way of doing it. So we're going to be looking at both of them and just see, what you can look for as a customer or at your customer's facility, what you can look for to make this easier. We'll start with, a non-productive today. We'll look at, all the different categories under that. And then at the last end, we'll quickly look at leaks. We all have leaks. We know how bad they get. A factory without leaks does not exist. So let's start with that 20%, which is the non-productive uses. So what do you need? Where do you start? So first of all, I always say that if you can't measure it, you can't manage it. So if you don't know how much air you're using, how can you improve on it? So flow meters is really important. If your factory or your customer's factory is currently measuring the flow, that's great. If they're not, then I would advise you to promote flow meters. So, because if you have a flow meter on a machine that's using, let's say, 20 SCFM, that's your baseline. That's where you can see, can I improve it to 15? Can I improve it to 10? If the machine is stationary, you can see if there's a leak. If that flow meter is showing there's 3 SCFM going into the machine, but it's not running, then something is consuming air. So you need to measure it to be able to manage it. What we also need is, we need to know what is the minimum amount of pressure that the factory needs to run. You need to know your pressures. You need to know what your flow is. Once again, that comes back to flow meters. You need to know the cost of your electricity. So how much is the factory paying per kilowatt hour? If you don't know, and it's not easy to find, a nice baseline is normally about 10 cents per kilowatt hour. We've had 5 cents, we've had 20 cents. Sometimes you can Google, see that area of the country, where it is, what the kind of average cost of electricity is for your production facilities. But normally accounting or someone will know what that rate is. And then, and this is something we can provide. It's an Excel spreadsheet. We call it our SMC cost calculator. And all that information that you have over there, you can plot into that calculator. And we'll look at it shortly. And you'll put all that information in, and you can actually see what kind of dollar amount that air consumption is costing the company. If you need actual components, as you'll see there, I've got the flow meters in there, pressure switches, gauges. In the bottom corner, this is items that we as the conservation team have. We have little data loggers with flow meters and pressure switches. So what we could do, if you have a problem with the machine and it's a little beyond the scope of what you've learned here today and what's available to you, we could come out and put one of these units in and measure your flow, measure your pressure, and actually graph it out and see what that machine is doing, or what that area of the factory is doing, and why you're having pressure or flow issues. Sometimes you'll find that one machine comes online and then you have a pressure spike in other machines, or pressure drop in other machines fault out. The little unit in the black case here is a little mobile flow meter that we have. There's actually a part number for that, and it has a battery inside, so you can just stick it into a machine, see what your flow is, and actually measure it. So it's a little mobile flow meter. Come to the calculator that I discussed earlier. This is the calculator, and I can email you guys a copy of this. It's actually really nice and easy to use. You put your hours per year, and if you look at the top here, there's hours per year 8760. That's 24/7. So whatever the factory is running, how many hours per year that machine is running, you put that value in. You put the cost of electricity in, and you'll put the flow rate that your flow meter is giving you, or if you know what the flow is already, you put that value in, and it'll give you an annual cost of the air. And in the second part, let's say, for example, you fix some leaks and now your flow is 7. You put that value in, and it actually shows you how much you're saving now. So if you need to go to upper management and justify something, this is a nice calculator to have. Say, look, I fixed this, or I can fix this, and we'll be saving this much money. Because in all honesty, if I go to someone at a company in upper management and I tell them, you guys can save 100 SCFM, doesn't mean anything to them. If I tell them you can save $20,000 a year, then suddenly people sit up. So this is why we use this calculator. It's a nice way of putting it in a format that someone that's not technically inclined would understand. So we'll just dive in and start at the first one, which is inefficient air delivery mechanisms. And that's a nice way of saying it's normally air blow. It's little blow knives, nozzles. It's mixing liquids with air, ejecting products from a conveyor belt, move, cool products, dry something that needs to be cleaned or was cleaned. And it's expensive. It's expensive. Air blow is expensive. Things to consider: sometimes you can't get away from air blow. And some factories put in fans, to blow things dry. There are many ways of doing it, but if you can't get away from it, just keep in mind that check the pressure. It doesn't need maybe to be at 70 psi. You could probably get away with 30 psi. Adjust the pressure down until stuff doesn't work anymore, and then adjust that up. If they're not in use, shut them down. We often walk through factories, and someone would say to us, oh, this area hasn't been in use, or we haven't run production during 2 weeks, and we walk through it and you'll hear air knives blowing all over the place, and it's costing the company money. Make sure your mounting is proper. It might be too far away. It might not be at the right angle. We've seen instances where one air knife used to be fine, and they've added like 3 or 4 other air knives just because it wasn't, aimed properly at the product. Just make sure it's close enough, it's in the right position to get the most effective flow on that. Other things to consider is, high efficiency nozzles. We have nozzles that as they blow out, they actually take some ambient air and actually add it to the nozzle, as you'll see in the picture below here. It has holes where it sucks in, and also at the same time it's OSHA certified because of those holes. Remove any unnecessary air knives. If you can mount them properly, you can remove the other ones. And if you can automate shut off on air knives, that is normally something that we would strongly advise. If you can get an output somewhere, even if it's from the conveyor belt, from the conveyor motor. If the conveyor stops, the air knife stops. If the conveyor starts up, the air knife starts up again. And this could be as simple as just putting a two-way valve in, probably $25 to fit a valve like that, and just get it onto an output somewhere on your line. Once again, if you have a flow meter and you can measure what your air knives are doing, you have a baseline to start from, and you can work from there. To quickly look at the circuit of an air blow circuit. This is just I mean, there's a lot of formula, but it's outside the scope of today's presentation. If anybody wants more information, I can send it to you. We'll just have a shuttle valve. We'll have a filter regulator. One of, obviously filter out particles that can get blown onto your product. And number two, to set the pressure as low as possible. A two-way valve to shut off the air, start it up again, and then a high efficiency nozzle. That'll be a basic setup for how airflow circuit should look. If we look at the actual piping, why do we need a nozzle? This is just a quick graph to show that if you have an open blow, air pressure as it goes open to atmosphere, it'll drop in pressure. A nozzle actually causes a kind of back pressure that you would need. So it'll have maximum pressure right up to the nozzle before it blows up. So you actually get more force with a nozzle than without a nozzle. And then often you'll find people think like, the bigger the hole, the more I get. It's not like that. The more flow you get, but it doesn't mean your impact pressure would be exactly the same. And there is a calculation for it, which I can send to anybody that would actually need it. But yeah, just drop me an email if you need that information. Considerations that we can have. SMC has a pulse valve. And what this pulse valve does, we have two of them actually. The one's mechanical and the one's electrical. And the theory behind it is, if you pulse really quickly, even if it's twice a second, if you pulse really quickly, in the time that air pulses off, you actually have a pressure buildup behind the nozzle, and as the valve opens, it blows out. So you actually have spikes, as you'll see in this pulse flow. You actually have these high spikes, and then you have zero airflow, and then you have a high spike and zero airflow. And that's actually more efficient than just a constant blow because of that puff of air. And these are adjustable, and you can actually adjust them to whatever pulse you want. If you want it to pulse really quickly with small breaks in between, or pulse every once a second with 1 second off, it's all adjustable. And if you plot all those values into our calculator and you look at it, you can actually see how much air you can save. I just did 50-50. If you switch on for a second and switch off for a second, that's a 50% save. If you have it on 70%, 30% off, like, off for a second, or on for a second and off for half a second, there's obviously like a 30-25% saving, or whatever saving you can do by just pulsing it. And these are very advantageous if you can use these in parts feeders, for example. If you feed parts, we don't need a constant blow. You just need that puff of air just to get parts moving into a conveyor or out of a parts feeder. It's something to consider. Looking at the two that we have, the mechanical one, that one is actually pretty nice. It's very easy to retrofit. You just put it in the line. The moment it gets air pressure, the airflow going through it causes the pulsing. The moment you cut the air off, it stops pulsing. Very simple to use, very easy to implement. It's got two little set screws, on and off set screw. And if you set those to whatever values you want, you can set your on-off pulse, or your duration of your pulses. The electrical one, it's a bit more difficult, obviously, to implement. You actually need to set it onto the PLC or somewhere where it's going to get a signal from to start pulsing and stop pulsing. But it's a lot more programmable. You can set it to pulse. It gets a signal, a pulse signal. It'll pulse for 5 seconds. It'll stop. It'll pulse 10 pulses. It'll stop. It's very customizable. These were actually designed to use with our ionizers, so where you can puff ionized air onto products with static electricity. So that's what they use for mostly, but you could use them on air knives. There's no reason you can't. So both of those, we have videos available. If you want more information on them, once again, just drop any of us an email and I can get that out to you. Energy intensive applications. Once again, these are products. There's nothing wrong with these applications. There's sometimes just a better way of doing it. They use a lot of energy compared to the function that they do, and there might be cost-effective way of doing it. One of the big culprits is Vortex Coolers. And for those who don't know what a Vortex Cooler is, it's basically air blowing into a panel with a vortex effect, sucking out the hot air and putting cold air into the electric panel to cool it down. These can be replaced with those little AC air conditioner units that cool your electric panels. They are very cost effective. They're very cheap to run. The Vortex coolers, what we often find is they never shut off. They get installed. There's a ball valve on them. Someone opens the ball valve and they forget about them. The machine is shut off. No one's running it, but the air was never closed off to this Vortex cooler, and it's still cooling the panel, even though the panel is shut off. Now, what we suggest doing, if you have to use a Vortex cooler, think about a solenoid valve, maybe connected to a thermal sensor. If the panel is cold, don't cool it. If the panel gets hot above a certain level, the Vortex cooler turns on. We very recently saw one that was outside in the middle of the winter. It was ice cold. We were freezing. The Vortex cooler was cooling a panel. It was freezing outside. So just keep in mind, no one ever shuts these off if they're not on this, if they're not on a timer or on a if they're not connected in some way to automatically shut off. They very seldom get shut off. Vibrators, something else that we find that consumes a lot of air. These start at about 5 SCFM, and they, the sky's the limit with them. You get very large ones. They're very loud. They're very expensive to operate. If they keep on running, sometimes they affect other components on the machine from the continuous vibrations. Just have a look, if there's something else that can be done. We've found in the past where vibrators were fitted on machines and it wasn't, stuff wouldn't feed properly through the machine. So they added a vibrator just to see if it'll help. It didn't help, but no one ever removed the vibrator, so it's still there. We could do that in a different way. You could put air shocker cylinders on. It's just a little cylinder. It sits on the side of a hopper, and it just gives it a knock as it gets pressurized. So it's just like, imagine a guy standing there with a hammer, just knocking the hopper. The cylinder does exactly the same principle. It just hits it on the side, and the product gets moved inside. If you have to use a vibrator, put a flow control on the exhaust port. These little exhaust flow controls, they work very well. And turn down the flow. Turn down the flow on that vibrator once again until someone starts complaining, and then just turn the flow up slightly. So we always say just turn it down until someone complains, and then you turn it up a little. Blowguns, another big culprit in factories that consume a lot of air. And we find a lot of leaks on blowguns too. Always keep in mind, your blowguns have hoses attached to them. That's where we find a lot of leaks because they are handled a lot. Blowguns themselves consume a lot of air, and it depends on how often they are used. These ones that you'll see there in the bottom corner, the silver ones, those just, that's kind of what you find in industry a lot of the time. And they start at about 25. I've seen ones that consume 50 SCFM of air. And that's a lot of air. You can consider replacing them with an energy saving blowgun. We have ones that I think the average is about 7, and the higher end is about 9 SCFM. And if you use it in conjunction with a high efficiency nozzle that sucks in ambient air, you'll find that you'll get quite a bit of impact pressure out of them at quite a reduced flow rate. Another product that we recently have is what's called an impact blowgun. So what these do is, it's the one in the corner with a little graph next to it. They have a little tank in the handle. So what happens is air rushes into it, charges up that tank, and the moment you pull the handle, it's like a puff of high pressure air because it's built up in the tank. And they'll give you this, if you look at the graph, they'll give you this sudden spike, and then they'll just bottom out like a normal blowgun. And what those are very good for is if you just need like a puff of air to clean off a work area, if you just want to puff stuff out of the way, if you're going to be cleaning the floor or cleaning the machine from dust all over, these probably won't work that well. But if it's like a milling machine where there's a lot of little metal shavings and things, you just need to clean it, really quickly. These work really well with that high puff of air, and they use a lot less air. I think the average was about 2 SCFM on these, just for that puff of air. So keep those in mind, they are available. Diamond-based drains, which is also a big user of air. If you walk through a facility, you'll find these most often at the bottom of your compressor tanks. Or if you have the storage throughout the facility, tanks in different areas, just look at how those are drained. If it's a timer-based drain, they can go either way. They are very expensive to operate because how these work is you set your time on, your time off. So once an hour, it might come on and blow off for 1 minute and then shut off again, which is great if you have exactly that volume of air. But let's say your dryers are working very well. You don't have any water in your tank. So what's going to happen? It's still going to be blowing off for a minute. So for 1 minute, you're going to be blowing air into the atmosphere out of your tank for no reason at all. The other side is also true. You might have a faulty dryer and you might have a lot of water coming into your tank. Once again, this is only going to blow off for X amount of time. What might happen is there might be a lot of water in that tank, and 1 minute is not long enough to empty it. So there'll be some water left, and each time there'll be a little bit more water left. We went into a facility one day where they said we have problem with with pressure and flow. The moment our machines come online, we don't have enough air, and half their tank was full of water because one of these weren't blowing off for long enough. So look for these. You'll find them quite often. You're just at the bottom of the tank, a little hidden out of sight. What we would suggest considering is a float-based drain, where you have the drain at the bottom of the tank. As the water fills the little drain at the bottom, the float lifts. It blows out the water. When there's no water to keep the float up, obviously it closes down, and you don't have any. So this will blow off for as long as there's water, and if there's no water for 3 weeks, it won't blow off for 3 weeks, unlike the timer-based drain. Vacuum generators, when we walk through facilities, these mess with our equipment quite often because they sound like leaks, but they normally just vacuum being kept on and not shut off, when it's not in use. If it's an electric vacuum pump, that's fine, because electric vacuum pumps obviously don't use compressed air to generate the vacuum. But if it's a Venturi style unit where it uses positive pressure to create the vacuum, and they don't shut it off, that obviously consumes a lot of air. They need to be shut off. They need to be automated to shut off. If it's not needed, shut off the Venturi. Don't leave it on. Consider an electric vacuum pump if it's a lot of vacuum cups that you're using. If it's just a small application that doesn't, get used all that much during the normal cycle of the machine, a Venturi is fine. You don't need to invest in an expensive electric vacuum pump. We will also have energy-saving Venturis where they go through multiple stages inside, a 3-stage or a 2-stage. Keep those in mind. They are out there. They are a lot more effective than just your standard Venturis. There are more effective Venturis out there. A good example that I found one day, I was auditing a facility, and they wanted to save on their electricity bill. So they decided to remove all their electric vacuum pumps and install Venturis. So in the first picture, you'll see the electric vacuum pumps that they had. In the second picture, big empty hole, small Venturi, did the same job, and they were very happy. But when we did the math for them, the electric vacuum pumps were running, 24/7. The Venturis was also running 24/7 because whoever installed them installed the pipe before the FRL, which means even if when the machine's air was shut off, the Venturis were still running. So we did the math, and the annual cost to run the electric vacuum pump was $1,576. To run the Venturi was $2,800. So by trying to save electricity by using air, they actually lost $24,000 a year with 19 of these. So it's easy to go wrong by thinking I'm saving on electricity by replacing it with air. But as we saw right in the beginning, 85% of your electricity is lost in heat when you generate compressed air. So you only get 15% of that electricity into compressed air. So it's only 15% efficient. So it's not as efficient as electricity. And we are in the business of selling pneumatics. So we do like customers buying pneumatics, but we also, would like to advise them on just, how to save on their energy. Overpressurized applications. This is something we find quite often, and just, basically said, it's the regulator is cranked up all the way. The machine can run at lower pressure, but for some reason it's running at a really high pressure. And we normally look at those. We find them all the time. We find them on air knives. We find them on, like I said, vibrators. At some stage, something was wrong. Someone tried to just up the pressure on the machine to see if it solved the problem. It might have solved the problem for a little while because there might have been a faulty actuator on there and the machine kept running at this higher pressure. They replaced the actuator, but no one turned the pressure back down to the machine's actual OEM pressure requirement. So keep that in mind. If you see a regulator at line pressure, what the rest of the factory is at, keep in mind that something is not right. Why is this machine at line pressure? Just investigate, see if there's some way to set the pressure down. It might not be necessary to run that machine at that pressure, or compare it to the machine next to it. If there's another machine from the same manufacturer that does exactly the same thing, similar machine, have a look at it, see if the pressures are the same on all these machines. I've walked through factories where there's 5 similar machines at 5 different pressures. So, and just pick the lowest pressure. If machine 1 can run at 60 psi, why is machine 3 running at 75? So just set the pressure down and see. You more often than not find that the machine will run fine. Sometimes you'll have an application though. You'll have one machine that requires, let's say, 60 or 80 psi, and the rest of the factory is running at 60 or 70. Just have a look. Is the whole factory now running at that pressure just for one machine? We had a facility that we visited recently that the whole factory was running at 95 psi because of one palletizer. One palletizer in the whole factory faulted out at 90. So they set up the compressors for the whole facility, and I'm talking about a massive facility that run at 10 psi higher, just for one machine. So have a look at why you need that high pressure on that machine. If you do really need it, consider something like a booster, where the rest of the factory is running at a lower pressure, and this machine, the pressure is boosted just on this machine to, a higher pressure. And if it's an intermittent use, even better. Then you can just put a booster in the line with the tank, store high pressure, and when it's required, the machine can draw from that tank while the rest of the facility is running at a lower pressure. Overpressurization on actuators. This is the smaller, easier fixes. Lots of the time, actuators push something out. They'll move something, they'll retract, and they'll sit there. The retraction doesn't need real high pressure. So what you could do is we have these sort of like flow controls, but the flow control actually retracts the actuator at a lower pressure. If it retracts at a lower pressure, obviously air expands. You use less air to retract it at a lower pressure than you do at a high pressure. So you can set all your cylinders to retract at a lower pressure. If you can use spring actuated cylinders, obviously that's even better. So the 3 ways that we normally look at retracting actuators at a lower pressure to conserve compressed air: obviously spring in the bottom, as we just discussed, putting a pressure regulator on the port that doesn't require high pressure if it's just moving a heavy part. And then the other way, which is a little bit more complicated, is using an exhaust return circuit. And what we do with that is we actually take the pressure that is exhausting from the actuator and redirects it to the front of it and retracts the cylinder with it. It's all standard components. There's nothing really special to do. It's just building the circuit in a way where the exhaust air goes to the front of the actuator. You might need an extra check valve and a flow control, but it's actually just a circuit. And if anybody wants a copy of that circuit, I can provide it. We can even run through the circuit with you and have a look at it. These work best on really large actuators. The smaller the actuator, the less the savings would be. But if you have a 200 bore actuator, it consumes a lot of air on the retraction, so you could reuse that exhaust air. Idle mode savings. Once again, idle mode is, when you walk through a factory, that machine is standing idle, it hasn't been used in a week, but it's pressurized. How can I save on that air? Obviously, the best way is shut off the air to the machine, but that's not always possible. Sometimes it's just a lunch break or a tool change or a breakdown somewhere else in the line, and the machine is sitting there idle for a few hours, and no one really wants to shut it off because it might be time consuming to get it up and running again. Some machines have clutches, some have actuators that'll extend, and then people have to manually get those actuators back into their startup positions. There are multiple ways of doing it. Okay, obviously, the first way was a two-way valve, shut all the air off, the machine doesn't run, doesn't consume any air, none of the leaks are leaking, so that's the largest saving that you could possibly have. Once again, a flow meter. If you don't have a flow meter on the machine, you don't know if it's consuming air. It might be sitting idle and not consume any air, which is great, but most machines have leaks, and most of them will consume air when they sit there. So if you can have a flow meter on the machine, that is the best way of doing it. Two-way valve, shut off all the air to the machine. Also, the most cost-effective way. But if you can't do that, then we have a valve called the standby valve. And what the standby valve does is, while the machine is sitting idle, it'll drop the pressure on that machine. So it's connected to a little flow meter. It detects flow. So if there's flow going into the machine, the standby valve is running at whatever the set point is, which might be 80 psi. The moment there's no flow going into the machine, or the flow is below a certain value, it'll receive a signal and will drop the pressure to a standby pressure, whatever is the minimum required pressure to keep all the actuators where they need to be, to keep just to keep the machine in a standby mode, in the idle mode. And that might be 30 psi. Once again, air leaking out of a little orifice at 30 psi is a lot less. That leak is a lot smaller than that same pressure coming out of that leak at 100 psi. So you'll save quite a bit on leaks and idle time. These are very popular in applications where there's a product that cures. For example, a car tire. There's a process where the tires are cured in the factory, and these standby valves are excellent for keeping standby pressure during that curing period. And then the moment air pressure is required again, these go up to whatever the set point would be, 80 psi, and the machine would operate at 80 psi until the next tire is starting to cure. It'll drop the pressure to 30 psi or 20 psi, whatever the standby pressure is. So these can save quite a bit. The picture that we have here is our high-end unit, but we also have a much more basic unit where it's just a regulator that you can set to a lower pressure and a bypass valve. So I'm not sure if those are available yet. Machine idle time. Once again, if you don't have a flow meter you can't measure, please keep that in mind. Consider considerations. Remove the pressure. Check if there's a shut-off valve on your machine that you can shut it off, and if it's on, measure and see. If you get quite a bit of flow while it's idle, see why you're getting that flow. That flow might be leaks or air knives being on. There's a lot of reasons that can be there. Large consumers of air, which is the last section on inefficiencies that we have. Large consumers of air is all those machines in the factory that use a lot of air, for a short period of time, and they can cause quite a bit of havoc in your compressor room without anybody knowing. We have found quite a few times where there's a machine that uses a lot of air for a very short period of time. And when it uses that large volume of air, it sucks it out of the main header. And what happens with your compressor when you have that huge amount of air being sucked out of the header for like only for a second or two, 2 seconds, 3 seconds, what would happen is you would have a pressure drop. So the system pressure will drop, as you'll see in the top line there, the brown line. The pressure will drop, and what would happen to your compressor? Your compressor would think, oh, wow, I need more air. So the compressor will start loading. It'll start ramping up. And it'll hit it really quickly because it was a very short period of time that air was required. So it'll build up pressure really quickly and it'll start unloading again. And as you'll see on this graph that we have here, this was loading and unloading like every minute. This compressor was loading, unloading, loading, unloading, because this machine was drawing so much air out of the line. And there is a way to solve that problem. We call this a air management system, and it's something you can make up from existing components. So what we have is we have a tank, we have a flow control in front of it, we have a pressure regulator after the tank, and we have a check valve. So, and how basically how it works is you have your flow control that gives you a steady flow into your tank. So let's say that tank's full of air, and the pressure regulator is set to the minimum amount of pressure that this machine needs to operate. The moment that machine needs a lot of air, it's not going to pull it out of the header. It's going to pull it out of this tank. But this tank's obviously going to have a pressure drop, so air is going to flow into this tank. The flow control causes that air not to rush in there, not to have a huge rush of air going into the tank, dropping pressure in the main header and having the compressor start loading. So air will flow in steadily. So let's say this machine cycles, needs a lot of air every 2 minutes, for example. You can set this flow control to fill that tank in a period of less than 2 minutes, but a steady full. So you could set that to a minute. So it takes a minute to fill the tank. Every 2 minutes, this machine cycles. So it cycles, takes a minute to fill the tank. A minute later, the machine cycles and it draws the air. So just to get that steady, slow flow so the compressor doesn't see that huge pressure drop. The reason we put the check valve in there is you don't want the machine next to it to steal air from it. So if other machines in the line, requires air, it might not be as much as this one. Air flows wherever the pressure drop is. So if there's less pressure on the other side of this tank, air is going to flow out of this tank back towards the check valve or the flow control side. So we put the check valve in so air can't flow back and other machines can't steal air from it. The picture here that we have in the corner up, that is a SMC unit that we have. It's got all the nice bells and whistles on it. You can get them more simpler than this, but this one has pressure switches and flow switches and all of that, so you can monitor exactly how much air your machine is using and at what pressure it's moving it. I just threw in this graph quickly. We installed one of these at a factory, and as you'll see, the before and after. Before, the header was all over the place, the blue line right at the top. The flow into the tank, they didn't have a check valve and they didn't have a flow control. They just had a tank on there. You'll see it was all over the place. At the moment the machine cycled, a lot of air rushed into that tank. And then they had a robot right at the end of the line that this tank was supplying. That was the green line. You'll see the huge pressure drops on there. And when it got to a certain level, it actually faulted out. So we installed a air mass like this, check valve, flow control tank, pressure regulator. And this is what we had after. So the first, hour or so, it's a little bit all over the place because it takes a little bit of time to fine tune it, to set your flow at exactly the correct going into the tank. Making sure it's running, it doesn't use more air than it does. But as you'll see, the pressure to that robot became extremely steady, the green line, very steady. Halfway through, you'll see when we got it really fine-tuned, how nice and steady the blue line was at the end. It was a little bit up and down because it was still filling the tank, but it was nothing as much as it was before, where it dropped 10 psi at sometimes. So really steadied out. And the airflow into the tank too, still air flowing in and out. Obviously, the graph goes up and down, but nothing as volatile as it was before. So really steady and a really nice flow on that. Dryers, we all have these. Not everybody has desiccant dryers. Desiccant dryers are a huge user of compressed air, especially on the purge. For those that don't know, the dryer has two towers. It dries the air going through one tower, while it uses air to dry the desiccant in the other tower. So then it switches over, and once again, moisture is removed in the other tower, and it switches back and forth. And it uses compressed air to get the moisture out of that desiccant, and a lot of that air is just obviously just purged out to atmosphere. About 20% of the air going into that desiccant dryer is purged normally on a normal time-based unit. So the thing with desiccant dryers is they are often set on a timer. And the timer would say it'll take 2 minutes to dry the desiccant. So we're going to be purging for 2 minutes through this tower. So air is just blown through it once again, like we had with the timer on the tanks. It might be needed. 2 minutes might be enough to purge it. It might not be enough. So it needs to be set accurately. It needs to be changed for different periods of the year, and someone needs to monitor it all the time. But maintenance staff gets busy, and this never happens. And also you can use external heat to heat the air, so hot air obviously purges more efficient than cold air does. So this little table that we have here, we just showed a normal desiccant dryer that's on a timer. So the other option being dew point, it actually measures if there's water in the air. So this one is on a timer, and if you look here, no heat on it. For 2,000 SCFM, it costs them $30,000 a year to dry the air. This is how much they lost. If they had some heat on there, an external heater, it went down to like 23,000. So they saved about $6,400 by just heating the air. If we go to dew point control, which is actually sensors that measures how much air is water is in the air, and it purges only for the period of time that it's required, that's a very different picture. Heatless, still no heat, it drops to a 50% saving. It's 15,000 if it's on a dew point versus on a timer. If they add some heat, it goes down to 8,000. Compare that to 30,000 that same desiccant dryer was using before it had dew point control. So that makes a big difference. And you can normally hear these blow off. I stood next to one day in the facility. It vented for 20 minutes. Eventually I got tired and I left. It could have vented for another 40 minutes for all I knew. It was just venting. And I don't know how much air they were using on that machine. It was impossible to determine. It was just too much. Have a look at these. Stand next to your desiccant dryer. If you want to time it. Look on your watch how long it vents. Have a look at the pipe. If you have a flow meter and you can stick it on the purge pipe, that'll be give you an accurate amount of how much purge you're having on that machine. I always say, if you hear blow, if you can hear the air blow, it means money is being blown to the atmosphere. Walk over it and go and have a look. Which brings us to leaks. We'll only have a few more. I'm not sure how we are on time. Okay, we've got a few more minutes. Leaks. That is the most cost-effective. The best way to save money in your facility. It's the easiest fixes normally. You'll normally find a $20 fitting or a $5 fitting, saving you $300 in air leaks. This is a nice little chart just to show you discharge through an orifice. If I have a 1/16 hole, at 70 psi, that's going to be $590 a year. That's just, I've never seen a 1 inch, which is at the end of the spectrum, at 70 psi being $145,000. So I've seen a lot of 1/8s. We've even seen some 1/4 inch ones where they just blow off, and they'll blow a whole year. They'll just use them as an air knife without a nozzle. And that's kind of the kind of rate you're looking at. At 70 psi, $9,000. That's not unheard of. Keep it in mind when you hear air blowing, walk over, have a look. So when you do a air study like this, we advise doing a dew point check. Water in your components is never a good thing. I mean, like I said, if your oil's dirty in your car, you're going to have components failing. If your air is dirty, you're going to have components failing. The dew point measuring tool that we have, we can come out and measure your, the dew point if it's within reason of traveling. And you need to know that your air is dry and clean. The other unit that we show in this little picture here is the air quality filter. And what the air quality filter does is we just stick it in one of your lines, where there's no filtration, like a drop down. And we'll just see, we'll leave it to blow through a 0.45 micron filter into the atmosphere. And we'll see whatever gets stuck behind it. And you'll see in this one picture, there's some spots on this element. And that's oil. So that gave us an indication that there was something wrong with the compressor and oil was in the line. It could have been a lubricator, but in this case, it wasn't. It was actually a faulty compressor. And we found it. We sometimes find scale, and if the lines had water in before and they dried out, and then metal pipes, we sometimes find rust in them. And you find lots of different kinds of debris in there. The other picture was one of the worst ones we ever found. There was a lot of water in the line, a lot of scale, and a lot of rust. It actually got so bad it blocked up the whole filter. So we had all this running out of there. So it's good to find out what's in your line and to see what is the quality of the air going into your components. Fittings and tubings, that's where most of the leaks is that we find. And the thing with fittings and tubing is more often than not, it's environmental. We find tubing being used outside that isn't UV resistant, and it cracks and it breaks. We find chemical areas where they have a non-chemical resistant fitting or a non-chemical resistant tubing. It goes brittle, it breaks, it leaks. The seals inside these fittings that fit around the tube, around the tubing inside the fitting, those are not chemical resistant either. So they get brittle, they break. Even though the tube is still stuck in the fitting, the seal is not, around the tube, sealing around it anymore. Sometimes the tubing goes out of tolerance. Sometimes it's a low quality tube, from a not so well-known vendor. That's a little out of tolerance, and it leaks past it. If there's excessive pulling, pushing, that kind of applications, then you also find, over time, you'll start getting a leak there. So just have a look at contaminants in the air, look at, the chemicals, the environment. You'll often find that by just changing the fitting to the environment that's suitable, a suitable environment, then you'll have a longer life out of that fitting. Just some fun, how not to fix leaks. We always put this in because we find these in factories quite often. And the first picture, someone put a screw into a tube. They decided they didn't have a plug, so they just plugged it with a screw. That did leak. It didn't leak as bad as not having anything in there, but it did leak. And it was also a safety issue because there was 70 psi behind that little screw. If that screw came out of there with 70 psi of pressure behind it, it could take someone's eye out or hurt them pretty badly. The valve in the corner with a glove, they didn't have a silencer, so they just put a glove with a zip tie around it. So that was a makeshift silencer, and every time it was quite funny. Every time the valve exhausted, the glove would inflate and look like someone's giving you a high five. Zip ties with bend over tubing, we see that that's probably the most common fix we see. They remove a filter, they remove a component that's no longer required. The tubing is still there. They bend it over, they put a zip tie around it, and it stays like that. Those always leak. It's not a perfect seal. So they will leak, and the more there are, the more they'll leak. And if that zip tie comes off, then it's an open tube. And then good old duct tape. I always say that if you don't use it enough, if duct tape doesn't work, you're not using enough of it, but that does not count pneumatics because eventually it'll start leaking again. It'll always start leaking again. And what we normally suggest for these kinds of fixes is to suggest having a repair cart in the facility. You know, a cart with all the correct fittings, all the correct tubing. The maintenance, if maintenance goes to fix a leak, they take the cart with them. They get to the leak and they can fix it. What the alternative is, if maintenance walks out there, there's a bad leak, he doesn't have anything to fix it right at that moment. He has a roll of duct tape, he duct tapes it, he walks back, something else happens, and he forgets about that leak. That's in these facilities, it happens all the time. And the leak never gets fixed until eventually the duct tape doesn't hold the leak anymore, it starts leaking again. And you know, it's normally just a vicious cycle. And we have had a lot of success with these sort of, we call them crash carts, and with having a range of fittings inside, having a range of, you know, commonly used components inside, and having it inside the maintenance area where they can just take it with them, fix the leak, it's fixed, it stays fixed. Having the correct fittings on hand is normally a big plus. Air prep, once again, environmental. We have seen lots of filters and regulators that's corroded way beyond the point of the one in this picture. This was outside. It was a really chemical area, and it was leaking. So keep in mind, once again, environmental. If you need an epoxy coated filter regulator to install that, stainless steel, install that. It might be a little bit more cost upfront, but the savings in potential air leaks would outweigh that upfront cost. Actuators. If you see an actuator like this, if it's not already leaking, it's going to be leaking fairly soon. There's so much debris on it. If you look at the shaft there, the debris lands on that shaft and it gets sucked into the front, and it's going to start leaking on that shaft. Because actuators normally only leak really in two ways. It's either leaks on the shaft seal where the rod goes in. That's where it would normally leak because of debris getting sucked in, or side load. Sometimes there's a heavy weight on it and the side load wears out the seal and the bushing. So you'll find a leak there. The other place that you'll find a leak is internally on the piston seal. And those are a lot more difficult to pick up. What you'll normally find is you'll hear a complaint, or you'll find a valve leaking out of the exhaust port. And it'll just be blowing out of the exhaust port. And you'll replace the valve, but it'll still be blowing out of the exhaust port. Because what's happening is you're pressurizing the one side of this actuator. Air is passing over the piston, out of the front port, back towards the directional control valve and out of the silencer. So it's just leaking past. And I've had it where we've tagged filters, valves, and said possibly the actuator. And we come back the next day to continue with the assessment, and the night shift on maintenance had replaced the valves and it was still leaking. So normally if you hear an exhaust port leaking on a valve, it's the piston seal on the actuator. And we'll find those leaking for a long time because it's sometimes a lot more complicated replacing a larger actuator than replacing a valve. Just some considerations. If you have an area with a lot of debris, think about putting a boot on the rod. Stainless steel or chrome plated rods, those are available. We have heavy duty scrapers that'll remove particles so it doesn't get pulled onto the shaft seal. Those scrapers, we even have them for weld environments where they'll scrape off weld spatter. Misalignment, the actuator might just be misaligned. We sometimes advise that you go to your store, say which is the actuators you order the most of. You'll sometimes find this one we order it like 8 or 10 a year, and if you go look, it might be something simple like misalignment, and they keep on failing and they just get replaced, or some side load that's unnecessary. So just go to the store, ask them which components we use the most of, and you'll often find actuators that's pretty easy fix, just environmental or side load or something like that. Lastly, we'll quickly look at dust collectors and then we're done. We're good for time, I think, by about a minute. Dust collectors, these are big culprits. I've gone through facilities and where they've told us that, oh, we shut down for Thanksgiving and we were still using 700 SCFM. It's like we didn't know where it was going. And after doing the assessment and audit, we'll find one of the dust collector valves being stuck in the open position. Because when these fail, they fail open. Or when their pilot valves fail, they open the dust collector valve, the pulse valve itself. So whichever side of this fails open. And this might even be outside and might be just one of the tubes, running from the pilot valve to the actual pulse valve. Might be non-UV resistant. It might break. The moment there's a leak, that valve's going to get stuck in the open position. Air is just going to rush into it. And the problem is these are normally high up in the air inside the facility or outside on the roof, not in the area where you normally find them fairly easily. So when they get stuck open, you only realize you have a problem when you have a second compressor coming online, or accounting tells you, hey, we used a lot more electricity last month. What's going on? And you realize that all your compressors are running at 100% to keep airflow into the factory. And as you remember with that chart we had before, if you have a big flow like that, like a 1-inch, that could cost you up to $100,000 a year in air consumption. So if you have a big 3/4 inch valve like this stuck in the open position, that's a lot of air going into it. Some considerations, SMC does a 10 million cycle valve where normally valves are rated for like 1 million. This is a 10 million cycle valve. So this will last you a lot longer than a standard valve would. The other nice feature is it's a really can open really quickly, which means if it opens and closes quickly, it says a 35% reduction in the air consumption. So it opens and closes really quickly, gives you a really quick puff of air and shuts off. It makes a big difference, 35% on each, because these pulse quite often. Keep that in mind. Lastly, if you put a flow meter on your dust collector, it'll tell you that you have a leak. If your valve isn't pulsing and there's air flowing into the dust collector, obviously it's stuck in the open position. And normally, if you look at the readout on the dust collector's flow meter, you'll see it'll go to 0 or pulse up to a value, let's say 50 SCFM, and then it'll close to 0. And the next valve would pulse, it'll open. So it needs to drop to 0 to know that all the valves are closed. If you have it 50, goes up to 100, comes back to 50, goes back to 100, one of those valves is stuck in the open position. So I would suggest, once again, if you can't measure your consumption, you don't know if there's anything wrong. These dust collectors, it is difficult to find out if they're leaking. It's not easy to see one of them is stuck in the open position. So just in closing, keep in mind, if you can't measure it, you can't manage it. So if you don't know how much gas your car is using normally, and suddenly it drops to 7 gallons to a mile, then you don't know something's wrong. You can't have it investigated. If you walk through a facility and you can hear it blow, you can hear the noise from air, walk over, have a look, see if you see any of the items that we mentioned: air knives, an actuator, a valve blowing out of its exhaust port, a leak. Just hear why do I hear air blow? Because if air is blowing, there must be a reason for it, and there's a big savings potential normally. If you can hear it from a distance, it's normally a big leak. Ask your pneumatic manager or your parts manager. Ask them, what are the most common components you buy all the time, and have a look why. Why do these fail? These are very easy. They'll say, we'll order these actuators for those machines, once a month. Go to the machine and see why those actuators are failing. There'll always be air leaks. Keep that in mind. We can never fix all of them, but we can manage how many we have. So just keeping your hand on it, basically, and keeping preventive maintenance and fixing them at the time we find them, that helps a lot. And yeah, use the right component for the right environment makes a world of difference. And that's it. If no one's asleep, then or everybody's still awake. If you have any questions.
Well,
I
thank
have
you,
a
Johan.
question.
Yep, go ahead.
How can you detect? I've heard of using ultrasonic detectors to find air leaks.
Yes. So that's what we use. We have an ultrasonic leak detector with a big parabolic dish, and these are the ones that we use is accurate up to about 30 feet. Well, it'll be further, but that's I think what they say in the catalog. So jump and correct me if I'm wrong. So you'll hear the leak because it's set to 44,000 kilohertz. So the moment you hear that you can it filters out all the other sound and you can only hear the leaks. It sometimes does, it picks up other things too, like vacuum. So sometimes vacuum will mess us around. But yeah, that's what we use in a facility, and they are very effective in finding leaks. They are really effective. At least it'll point you in the right direction. And we found leaks up 30 feet up into the roof on main headers that no one knew there was a leak. And it must have been there for years because no one can hear it. It's too far away. It's up on the roof. And they do pick it up, yes.
The ultrasonic is an excellent tool. The problem, of course, is that you have to do it, right? There has to be scheduled time, and obviously it's very helpful if there's routine checks of the whole facility. The reason we argue that flow meters are also necessary is that the flow meter will tell you if there's a problem in an area, and then you can check it, and that saves you from checking areas that are fine, right? Otherwise, you have to check the whole plant.
We recently did a facility where they were shut off for the first day that we were there, about 2 weeks ago. And they had a flow, I can't remember the exact figure, but let's say it was 1500 SFPM that our meter detected. Our flow meter, they don't have a flow meter in, so they were never measuring their flow. And then when the facility started up, it went up to 2,900, something like that. So 50% of there was 50% flow while the whole facility was shut off, which means they were leaking 50% of their air. So yeah, we still have to give them the bad news.
Well, that's great. I appreciate it, Johan. That's great information. This was very detailed. This is exactly kind of what we were looking for. So if there aren't any other questions, I know we ran a little long. We'll go ahead and wrap it up. But just keep in mind that we are going to have them come back in April. We'll do our roundtable session. We'll do the breakouts. So we'll have a breakout room you guys will be able to jump into and delve a little further and ask any more questions that may come to mind between now and then.
Thank you, everyone.
Yep. So I appreciate everybody, and be on the lookout. We'll have the next invite coming out here within the next week. And everybody have a good day.